Dr. Clements. So as mentioned before, I will be presenting on a study completed on planet Mars. I'm going to begin with just some background on the planet. So Mars has a much harsher radiation environment than Earth does, and that can be attributed to two main factors. The first one is the lack of global magnetic field, which results in particles, charged particles will not be deflected by the magnetic field because it's missing. It also has a much thinner atmosphere than Earth, only 1% thickness of Earth's atmosphere, which again provides less shielding on the ground from the particles. There are two types of particle radiation at the top of Mars' atmosphere. The first one are galactic cosmic rays, or GCRs, which are very high energy particles whose fluxes are modulated by the heliosphere, which is all of our, from the sun, stretching out farther past Pluto. And they are 85 to 90% protons, 5 to 10% helium, less than 1% electrons, and less than 1% heavy nuclei. They have high enough energies that they can penetrate the Martian soil. The other type of particle radiation are solar energetic particles, or SEPs, which are produced in solar corona as a result of high energy processes from solar flares and the corresponding shocks from those flares. They're random and hard to predict, and the particles consist mainly of protons. There are two types of SEPs: soft events, which do not have high enough energies to penetrate the Martian atmosphere, and because they lose their energy in the atmosphere before hitting the soil. And then there are hard events, which are high enough energy that the secondary neutrons will reach the surface. So the purpose of this experiment was mainly focused on the risks of future manned missions to Mars. So the RAD measurements from this experiment correspond to all three stages of a typical mission to Mars based on previous NASA models. So it has data that corresponds to the outbound interplanetary travel, as well as the stay on Mars and the return journey home back to Earth. It also provides us a greater understanding of limits to preservation of organic matter, specifically at the Gale crater where the rover was dropped. It provides insight on how radiation may have affected possible previous organic matter on the planet, as well as how it might affect future life if we try to take that route. So, methods. The experiment took place. So this study took place between the 7th of August 2012 and the 1st of June 2013, which was one day after the rover landed on the planet. The RAD has a charged and neutral particle detector with multiple instruments, which can measure all ion species, as well as distinguish between the different species. Some of these instruments include a solid-state detector telescope, which measures the number of ions and electrons coming towards the spacecraft from a specific direction. It also has a CSI calorimeter, which involves CSI crystals and helps measure absorbed dosage. And lastly, it has a plastic scintillator, which generates photons of light in response to radiation levels. The experiment took place over around 300 sols, and each sol, which is a Martian day, is 24 hours and 39 minutes. During the maximum solar cycle 24, which is the most current maximum solar cycle. And dose equivalent for radiation is a physical quantity which they set in their experiment. It's in units of milligray, and it has to do with the absorbed dosage of the surface of Mars. So here is the first chart I have. It is the dose rate of radiation since landing of the rover. The dose rate varied between between, as you can see, 180 and 225 microgray per day. These daily variations can be attributed to a couple of factors, including atmospheric pressure changes. Mars has daily atmospheric pressure changes due to heating of their atmosphere, which I will discuss in more detail later. They also have seasonal variation, and the heliospheric structure variability due to solar activity and rotation also affects the daily dosage rate over time. Between the 12th and 13th of April, there was one hard SEP event, which caused a dramatic increase in dosage rate. And there are also four significant Forobush decreases on sols 50, 97, 208, and 259. And these were a decrease in GCR radiation because interplanetary coronal mass ejections served as a temporary magnetic field which deflected GCR radiation from reaching Mars. Any other smaller gaps in this graph can be attributed to the RAD measurement system being turned off so the rover could complete other activities without interference. These next two charts, the top one shows diurnal dose rates, so daily dose rates between sols 290 and 302, so it's an expanded figure from the one before. And it just shows in more detail how dose rates vary daily. And this is because, as I mentioned earlier, the daily thermal tides will heat the Martian atmosphere, which causes the mass of the atmosphere to redistribute. So less atmospheric column depth at a certain area will result in higher GCR radiation, which is what the second figure displays. It shows the comparison of radiation dose rate of the rover environment monitoring station to the atmospheric pressure measurements, which it also took. And the red is the measured dose rate, and the blue is the atmospheric pressure. As you can see, there's an anti-correlation between the atmospheric pressure and the dose rate. So less pressure will correlate to a smaller atmospheric column depth, which will, in result, have less shielding against GCRs and a higher dosage rate. So this next graph is a graph that shows the charged particle LET spectrum comparison. Now, an LET spectrum stands for linear energy transfer, and is the energy transfer of an ionizing particle to the matter penetrated by radiation. So the black triangles are the LET spectrum measured on Mars' surface, and the red circles are the LET spectrum measured during cruise inside the spacecraft. On Mars, the average dose rate after the Gale crater was 0.210 plus or minus 0.04 milligray a day. The cruise dose rate was higher at 0.48 plus or minus 0.08 milligray a day. The lower dose rate on Mars can be attributed to shielding of the lower hemisphere, which is provided by the planet. This shielding will actually reduce the dose rate by a factor of around 2. There are also interactions with primary GCRs with the nucleons in the atmosphere and soil, which will reduce the radiation levels. And the atmospheric shielding on Mars is thicker than the shielding provided by the outside of the spacecraft. This bar graph displays different dosage rates. So the first one is the annual cosmic radiation on Earth at sea level, and as you can see, it's between 0.1 and 1 millisieverts. This is on an exponential scale, and they did not provide the actual numbers, so by my best estimate. But the U.S. annual average from all sources is a little bit higher than that, and a typical abdominal CT scan is again higher than that, but you only get that if you need to every once in a while. The Department of the DOE radiation worker annual limit for a worker is again higher than that, between 10 and 100 millisieverts. But if you get over to the next column, you see that 6 months on the International Space Station per average is much higher dosage rate, close to 100 millisieverts. And then further on, you see a 180-day transit to Mars, which is again much higher than that, as well as a 500-day stay on Mars, which again is above 100 millisieverts, but not quite 1,000 millisieverts. So implications of radiations on microbials. Ionizing radiation is harmful to biomolecules. It actually is powerful enough to break molecular bonds in DNA, other organic molecules, and even water. It is possible that there is dormant life underneath Mars' surface soil. It is hypothesized that the survival clock of these microbials could be reset every dormant phase, which is how they survived radiation this long. Previous data has shown that it would take a 2-meter drill to reach these radioresistant cells, but data from the RAD measurements suggest it might only need 1-meter drill to reach possible radioresistant cells under Mars soil. The bulk of Martian atmosphere was lost 4 billion years ago, which left little shielding for radiation now. This changed the chemistry of soil and rocks on Mars because they went through those processes where their molecular bonds were broken, destroyed by the radiation. This makes it hard for us to tell if there was organic life on Mars because they have since been destroyed. If there had been, they would have since been destroyed since then. So in conclusion, humans, based on a typical NASA trip to Mars in a previous study, would acquire 0.10 sieverts of radiation based on this data from the RAD measurements. This dosage will not automatically kill you, but it is much higher than the average yearly dosage of 0.0062 sieverts. If there was an experiment done with humans and they were exposed to 4 sieverts of radiation, about half of them would die, and so that just gives you kind of a comparison. And in further conclusion, organic life hasn't been found yet on Mars because they don't have the materials up there to drill deeper into the soil. They're not sure if the radio-resistant cells are there, but that is kind of the next step because they could be dormant underneath there, and we can't get to that right now. The rover is actually mainly based out of the Gale crater as well on Mars, so there's also a lot of other places on Mars that they still have not gathered data on. And I would like to